Hello, gentlemen. This is Mr. Theodore coming to you today to introduce you to two new sections. We'll do these two sections in a series of videos. This first one will focus on section 3.1, in which we'll be solving a system of equations by graphing. The follow-up video, which you'll watch tomorrow, will cover section 3.2, which will talk about another means of solving a system of equations, that is, solving systems algebraically. The focus of this particular video, again, is on solving systems by graphing, and we're going to look at two main objectives in order to be able to solve a system of equations by graphing. The first of those two objectives is for you to be able to use your paper and pencil along with a straight edge to draw the graphs manually by hand. Once you're able to draw those graphs manually by hand, you should be able to interpret your graph to find the solution set of the system of equations. The second objective for this first video is for you to be able to solve a system of equations using your graphing calculator. So I'll show you how you can use the same sorts of methods to find the solution set of a system. However, you will not need to use your paper and pencil to draw the graph. We'll use the graphing calculator to make that process a little more efficient for us. So before we get into some examples, let's take a look at what solving a system of equations actually means. What is a system of equations? Well, a system is just a way of representing two similar scenarios using the same variables for each scenario, and then comparing those two scenarios to see when they will yield an equivalent result. There's lots and lots and lots of examples of times when we would want to compare two things that we're representing with an equation. One such example is in any cost analysis. So let's say, for example, we wanted to compare the price of a plane ticket with the price of a train ticket. We could write a system of equations that represents the cost of each ticket and graph that system to visually be able to determine what is the most cost-effective means of travel based upon how many miles we want to actually travel, and at what point will the cost of each mode of transportation be the same? Or essentially, at what point does it not matter cost-wise which mode of transportation you choose to take? And we'll come back to this example a little bit later. Let's start with a little bit of introductory information and go back and draw on your knowledge from Chapter 2, where in Chapter 2 we learned how to graph the equations of lines. And in Chapter 2, we looked at lines like 2x plus y equals 3, right? Or we looked at lines like y equals negative 5x plus 6. And what we said was, if we want to draw the graphs of those lines, we can find any one of the infinitely many points that satisfy that linear equation, plot that point, and use the slope to find all the remaining points on that line. And then we drew arrows on the ends of the lines to signify that those lines will go on forever, meaning there are more ordered pairs than just the ones that we plotted that represent solutions of that one linear equation. And when we looked at linear equations in the form y equals 5x plus 6, it was the same idea. We were able to take that equation, find any one whole numbered ordered pair as a start point, and use the slope to find all the others that would fit on the graph. And when we connect the dots to draw our line, we're going to draw arrows on the ends of those on both ends of the line to represent that the ordered pairs shown are not the only solutions of this linear equation. That the solutions do indeed go on forever because there are infinitely many ordered pairs that will satisfy the linear equation y equals 5x plus 6. So when we're looking at a system of equations, we're not looking at one line individually. What we're doing is we're taking two lines and we're going to compare them together. We're going to use the same variables for the two, and we're going to draw the graph of each of these two lines on the same coordinate plane. And what we're looking for is the point of intersection of those two lines, or in other words, the one point that satisfies both linear equations simultaneously. That one point that satisfies both linear equations simultaneously is what's called the solution of our system of equations. So if we were to draw the graphs of each of the two lines that we talked about earlier on the same coordinate plane, the arrows again would signify that there are infinitely many ordered pairs that satisfy each line individually, But in looking at the graph, we can see that there's one and only one ordered pair that satisfies both equations simultaneously. That point is 1, 1. And if we wanted to check to verify whether or not that solution or that ordered pair is indeed the correct solution of our system, we would plug the x value 1 and the y value 1 into both equations and verify that that one ordered pair is indeed a solution of both equations simultaneously. So now that we've drawn upon the knowledge that we learned in Chapter 2 to help us draw the graphs of two equations that were given in a system on one coordinate plane by hand, let's look at how you can make this process a little bit more efficient and use your graphing calculator to actually draw the graphs for you, and then allow the graphing calculator to calculate that point of intersection for you. This time we're going to use the equations 2x plus 3y equals 3 and y equals 2 over 5x plus 6 to create our system. And again, what we're going to try to do is use the graphing calculator to graph each of those lines individually and then analyze that graph to look for the point of intersection of the two lines, or in other words, the ordered pair that satisfies both linear equations simultaneously. Let's take a look at how you would solve this system on your graphing calculator. So if we go into our calculators, we know that to input an equation into the calculator, you would need to use the y equals button, which means we must convert all of our equations in our system to calculator-ready form. So if we take this top equation, 2x plus 3y equals 3, and we convert it to slope-intercept form, we'll get y equals negative 2 over 3x plus 1. So that's what we're going to enter for our first equation into the calculator. Y equals negative 2x divided by 3 plus 1. And the second equation in our system was already given to us in slope-intercept form. So if we go down to the y2 equation in our graphing calculator, we can input that equation in as well. 2x divided by 5 plus 6 is what y equals for our y2 equation. Now that we have both equations entered into our calculator, we can hit the graph key to visually see our two graphs. This looks very much like the graphs that we drew by hand in the previous example. The problem is, it may be difficult for us to determine the exact point of intersection when we're not actually plotting those points using the slope as we did when we solved this system by hand. So we're going to need to calculate the point of intersection if we're using the calculator to draw the lines for us. And the way we would calculate the point of intersection is we would first go to the calculate menu. So we're going to press second and trace. And we're going to choose option 5 because we want to calculate an intersection of two lines. So we'll highlight option 5 and it's going to ask us for the first curve. Now what the calculator is asking us for here is, what is the first line or curve that you want me to find the intersection of? And it tells you at the top of the screen, the cursor is flashing on the y1 equation, and it gives you the ordered pair on the y1 equation where the cursor is flashing. Right now my cursor is currently flashing at 0, 1. So I can choose any point on my first line by pressing enter to select my first line as the first curve. Well, it would seem that I have selected only one point on that curve, but in actuality I told the calculator to use the entire line. So now the calculator is asking me for a second curve. And so what I'm going to do is I'm going to choose any point on the second line or the y2 equation to select that entire line to tell the calculator, hey, this is the second thing I want you to find the intersection of. So you'll notice right now that my calculator is flashing on the point 0, 6 on the y2 equation, which was the second equation that I input into my calculator. If I hit enter to select any point on that line, again, I'm selecting the entire line. And what happens is I end up with a guess. That guess is really irrelevant. It's based on the points that I chose on my two lines. I can skip through that guess by pressing enter a third time, and it tells me the point of intersection for my system of equations. Right? The solution to this system of equations is the point negative 4.6875, comma 4.125. So as you can see, the graphing calculator would be useful here, particularly because the point of intersection was not a whole numbered ordered pair. And had I drawn this graph by hand, it would have been really difficult for me to determine the exact location of the ordered pair, since I would not be using whole numbered ordered pairs for the solution. So the final thing I'd like to share with you on this video is going back to that practical example. How would we actually create the system and solve the system graphically? So what I want you to do now is to read through the scenario, and I want you to press pause on the video and give yourself an opportunity to first see if you can come up with the correct system of equations that represents both scenarios, both the cost of the plane ticket and the cost of the train ticket. Press pause now to give yourself a moment to think of the two equations that would represent the cost of each ticket. So the equation you should have come up with to represent the cost of the plane ticket is cost is equal to $1 for every 25 miles traveled plus $60 for your luggage fee. Our slope, 1 over 25, represents the rate of change in our costs. Our cost will increase by $1 for every 25 miles traveled. This should seem very familiar to the slope section we covered in Chapter 2. The cost of the train ticket should be represented by the equation cost equals 2 over 25 times the number of miles traveled plus $50 for your luggage fee. In the second equation, the slope, 2 over 25, again represents the rate of change for cost. We are saying the cost will change by $2 for every 25 miles we travel. So now I want you to hit pause again. I want you to take a moment to draw the graphs of each of these lines and see if you can find the solution set for this system of equations and identify how that solution set might help you to determine which means of transportation you should take dependent upon how many miles you're going to travel on your trip. Press pause now to draw the graphs of each line. When you graph this system of equations, you should come up with graphs that look like this. For the cost of our plane ticket, we're going to use the black line. For the cost of our train ticket, we're going to use the orange line. And what we notice is, after 250 miles, both tickets have the same cost. So the solution to this system of equations is the ordered pair 250, 70. That solution represents, again, the number of miles traveled and the cost at that number of miles traveled, for which both modes of transportation are the same. So we can see from this illustration that if you were planning a trip that was less than 250 miles, it would be much more cost efficient to take the train. However, if you were planning a trip that was longer than 250 miles, it would be more cost effective to purchase a plane ticket. And so we were able to use a system of equations to compare the variables cost and miles traveled in both scenarios. And we were able to then use that information to identify what was the most cost-effective means of travel based upon how far we wanted to go. So in conclusion, from this video, you should have been able to solve a system of equations by graphing each equation using a paper and pencil. Much like we did in Chapter 2, again, we're going to identify the ordered pairs on each line individually and connect the dots for both equations. We're just going to draw both graphs on one coordinate plane. And for some equations, we may need to use a graphing calculator for a variety of different reasons, namely if the solution set is not a whole numbered ordered pair. And so you should also be able to use your graphing calculator to identify the solution set of a system of equations. When you come back tomorrow, we'll talk a little bit more about systems of equations, but this time we'll look at how to solve these systems algebraically.